Today we're diving headfirst into one of the most famous and, frankly, perplexing experiments in all of physics, the double-slit experiment.
That's the one.
You might have heard whispers of it, maybe even that it somehow proved human consciousness affects reality. But what's the real story behind this mind-bending phenomenon?
That's right. And that's our mission today. We want to unpack the core mechanics of the double-slit experiment, clarify some of these persistent misunderstandings,
Especially the consciousness one.
especially that one, yeah, and explore its really profound implications for how we understand reality, time, causality, even consciousness itself.
And we've got some interesting sources to draw from.
We do a fascinating Reddit thread, which always brings interesting perspectives, insights from Wikipedia, a quantum simulation, which is pretty cool, and then a deeper dive into a physics paper from Hendrix College and some recent research out of Hiroshima University.
Sounds like a solid stack. So get ready, folks. This might challenge a few things you thought you knew about how the universe actually works.
Definitely prepare for some moments, or maybe moments.
Huh. Probably both. So let's just get straight into it. What exactly is the double-slit experiment? Why does it keep physicists and, well, us scratching our heads?
Okay, so at its heart, it's pretty simple conceptually. You fire tiny particles.
Like photons, electrons.
Exactly. Photons of light, electrons, things like that. You fire them at a barrier, and this barrier has two narrow parallel slits in it.
Okay.
Then you just observe where these particles land on a screen placed behind the barrier.
Right. So what would you expect to happen, classically speaking?
Well, classically, it depends what you're firing. If you were firing waves, like water waves, think ripples in a pond,
Yeah.
or light waves, as Thomas Young showed way back in 1801, those waves would spread out, diffract through both slits simultaneously.
Okay.
And on the screen, they'd interfere with each other. You'd get this characteristic interference pattern,
Which looks like.
a series of alternating bright and dark bands. Where the wave crests meet, they reinforce, that's a bright band. Where a crest meets a trough, they cancel out, that's a dark band. Constructive and destructive interference.
Got it. Makes sense for waves. What about particles, like tiny bullets?
Right. If you were firing classical particles, say tiny little bullets or even grains of sand, you'd expect something much simpler.
Just two lines.
Exactly. Two distinct bands or lines of hits on the screen. One clustered directly behind the left slit, one clustered directly behind the right slit. They just go straight through one slit or the other.
Okay, that seems clear. Waves give you that interference pattern. Particles give you two distinct lines. Simple enough, right?
You'd think so, but then the quantum world decided to throw a massive wrench in the works.
Ah, here it comes. The weirdness.
Precisely. Here's where it gets truly bizarre. You take those particles, single photons, single electrons, even surprisingly large molecules like buckyballs.
Buckyballs, like those carbon sphere things?
Yeah, C60 molecules, quite hefty on a quantum scale. You fire them one at a time.
One at a time, so they can't possibly bump into each other or interfere classically.
Exactly. Enough time passes between each particle hitting the screen that they're completely isolated events.
Okay, so you'd expect two lines then, slowly building up, dot by dot.
That's the classical expectation. But what you actually see as these individual dots build up over time is the same interference pattern you get with waves.
Wait, what? Even one particle at a time?
Even one particle at a time, each individual particle lands as a single point, a dot. But the distribution of those dots, built up over many thousands of particles, forms those alternating bright and dark bands.
How is that even possible? It's like each particle somehow knows about both slits.
That's exactly what it seems like. Each particle, traveling alone, appears to somehow go through both slits simultaneously, interfere with itself, and then land on the screen in a position consistent with wave interference.
Okay, my brain hurts already. And this is where, as you mentioned, the whole observer effect and consciousness idea often creeps in, right?
Yes, this is probably the single biggest, most popular misunderstanding the experiment. People hear observer effect.
And they think, aha, my mind is changing reality.
Right. Or just the act of looking at it changes the outcome. But that's not what observer effect means in quantum mechanics. Not really.
So what does it mean then?
It means that the process of observing, the act of measuring which path the particle takes, requires an interaction. The particle has to interact with some kind of detector, some physical measuring device.
Oh, okay.
And that interaction is what changes the particle's behavior. It's a physical disturbance, not a mental one.
Like shining a light on something to see it inevitably warms it up slightly.
Sort of, yeah. Or like trying to measure the pressure in a tiny tire, letting a little air out. inevitably changes the pressure you were trying to measure. You can't measure it perfectly without affecting it. It's a physical consequence of measurement itself.
Okay, that makes more sense. Less mystical. So let's follow that. What happens if we do try to detect which slit a particle goes through? Put detectors right there at the slits.
Okay, so you set up detectors, maybe one at the left slit, one at the right. These detectors are designed to click or flash or somehow register if a particle goes through that specific slit.
Right. So now we know the path.
Now you know the path for each particle, and guess what happens to the pattern on the screen?
Uh-oh. Does it change?
Dramatically, the interference pattern completely disappears, vanishes.
No way.
Way! Instead, you get exactly what you'd expect for classical particles.
Two distinct
Three
lines.
distinct lines, one behind each slit. As soon as you gain the which path information, the particles stop behaving like waves interfering with themselves and start behaving like well-behaved little bullets going through one slit or the other.
So the very act of finding out which path it took forces it to take only one path.
That's exactly how it appears. By measuring the path, you fundamentally alter the quantum state. The wave-like behavior, the potential to go through both paths, collapses. You force it to choose.
You can see this in simulations too, right? Toggle the detector on, the pattern changes.
Absolutely. Interactive simulations show this beautifully. Detector off. Interference pattern builds up. Toggle the detector on. Poof. Two lines start forming instead. It's a direct consequence of the physical interaction required for measurement.
Okay, that's weird enough. But then there's this other layer, the delayed choice thing. This is where my understanding really starts to fray.
Ah, yes. Wheeler's delayed choice experiment. It takes the weirdness up another notch. Or several notches.
So explain this. If just detecting the particle changes its past behavior, what if you delay the detection?
Right. So imagine the setup again. Particle source, double slits, screen way back. But now, after the particle has already passed through the slits, but before it hits the final screen, you insert a device.
A device that does what?
A device that lets you choose at the very last moment whether you want to measure which path the particle took or whether you want to let it continue on unmeasured and see if it creates an interference pattern.
Wait, you make the choice after it's supposedly already gone through one slit or both?
Precisely. The particle is already past the slits, on its way. Then you decide, option A, insert detectors to find out which path it came from. Option B, remove those detectors and just let it hit the screen to see the overall pattern.
And what happens? This sounds impossible.
It sounds impossible, but it's been experimentally verified. If you choose, at the last second, to measure which path it took,
You get two lines, like it only went through one.
you get results consistent with it having gone through only one slit. The interference pattern is destroyed, even though your choice was made after the particle passed the slit.
And if you choose not to measure the path, let it hit the screen freely.
Then you get the interference pattern, as if the particle had gone through both slits simultaneously.
But how? The choice is made in the future relative to the particle passing the slits. How can that affect what happened back then? Does it change the past?
This is the crux of it. It seems like a future choice is dictating past behavior, and that just fundamentally breaks our everyday understanding of cause and effect, right? Causality.
Completely. So what does this mean for, well, reality, time, causality, everything?
It's a massive challenge to our fundamental assumptions, particularly local realism and naive realism.
Okay, break those down at local realism.
Local realism is basically two ideas combined. Realism is the idea that objects have definite properties independent of observation, like the moon is still there and has properties even when no one is looking. Locality is the idea that objects can only be influenced by their immediate surroundings, and that information or influence can't travel faster than light. No spooky action at a distance.
And the experiment suggests.
Well, experiments related to this, like those testing Bell's inequality, have pretty conclusively shown that local realism, as we intuitively understand it, is untenable. Quantum mechanics is non-local. There are connections that seem faster than light, though you can't use them to send information that way, which is a whole other rabbit hole.
Okay? And naive realism.
Naive realism is just the common sense idea that what we directly perceive is reality as it truly is, that the world is exactly as it appears to us.
And the delayed choice experiment challenges that because
Whether the particle behaved like a wave or a particle in the past seems to depend on a choice we make now or even in the future relative to that event. A choice that's causally disconnected in the normal sense. It suggests reality isn't fixed out there until it's, in some sense, measured or defined.
So the universe waits for the measurement before deciding what happened.
That's one way to think about it, consistent with the orthodox view. It implies this non-local creation of reality, not necessarily backwards in time causation, but that properties aren't fully real or defined until they interact in a way we call measurement.
Wow. Okay. Given these just bizarre results, how do physicists even try to interpret this? You mentioned competing ideas.
Right. Broadly speaking, there are two main camps, historically and conceptually. The realist interpretation, sometimes associated with hidden variables, and the orthodox interpretation, often called the Copenhagen interpretation.
Let's take the realist view first. What's their approach?
A realist fundamentally wants to say the particle always had a definite path. It went through the left slit or the right slit, even if we didn't know it. Its path was a real objective property from the start.
Okay, seems reasonable. But how do they explain the interference pattern then? And the delayed choice?
That's the massive hurdle. If it definitely went through one slit, why does an interference pattern form when we don't look? And how can a future measurement choice seem to dictate which past path it took?
Yeah, that seems like a direct contradiction.
It does. To maintain realism, you often have to introduce other concepts. Bohm's hidden variable theory, for instance, proposed that particles have definite positions and are guided by a sort of quantum potential wave. This wave knows about both slits and guides the particle, leading to the interference pattern. But this pilot wave itself is non-local and quite strange.
So it saves realism but introduces its own weirdness.
Exactly. And the delayed choice part becomes even harder to swallow for a strict realist because it really looks like backwards in time influence changing a supposedly fixed past property. Most physicists really dislike that idea, violating causality like that.
Okay, so what about the other side, the orthodox or Copenhagen view?
The orthodox view, championed by Bohr and Heisenberg among others, takes a radically different approach. It says the particle's path through the slits is simply not real until it's measured.
Not real. What does that even mean?
It means properties like which slit the particle went through don't have a definite value before a measurement determines them. The particle exists in a superposition of possibilities metaphorically going through both slits at once.
As a wave of probability.
Precisely. A wave function describing the probabilities of different outcomes. When you make a measurement like placing a detector at a slit, the wave function collapses. One possibility becomes actualized, becomes real.
So if you detect it at the left slit,
Then its position at the left slit becomes real at that moment. The possibility of it being at the right slit vanishes.
and this solves the delayed choice problem, how?
It avoids the causality violation. It claims the past isn't changed by the future measurement because the relevant aspect of the past which slit it went through similarly wasn't real until the measurement was made. The measurement doesn't alter a pre-existing past. It creates a specific aspect of the past record by making it definite.
So reality is only defined upon measurement.
In this view, yes, only measured events have definite reality. It suggests, as we said, a non-local creation of reality, but it frames it as reality becoming concrete upon interaction, not as future influencing past facts.
That's still pretty mind-bending, but it avoids the direct causality paradox.
It does. Think of quantum tunneling. A particle gets through an energy barrier it classically shouldn't have the energy to cross. The orthodox view says it doesn't have a definite position inside the barrier. Its wave function allows a probability of appearing on the other side, and when detected there, that becomes real. It never had to be in the forbidden region.
Okay, this hinges so much on the idea of measurement. We've established it's not consciousness, it's physical interaction. But can we define it more clearly? What counts as a measurement?
That's a fantastic and still debated question, actually. What constitutes a measurement? Niels Bohr had a useful description. He called it an irreversible magnification.
Irreversible magnification.
Yeah. Think about it. A quantum event is tiny, minuscule, a single photon, a single electron state. To register it, a measurement device has to amplify that tiny event into a large-scale, macroscopic outcome that we can reliably record.
Like the click of a Geiger counter.
Exactly, or a pointer moving on a dial, or a signal in a computer. That single quantum particle hitting a detector might trigger an avalanche of electrons.
Ah, the avalanche effect.
Right, creating a cascade that results in a detectable electrical pulse. That whole process is macroscopic and, crucially, irreversible.
Meaning you can't easily undo it, put the electrons back.
Pretty much. The process increases entropy. It moves from a specific, concentrated quantum state to a more spread out, disordered, classical state with a recorded outcome. Once that macroscopic record exists, the quantum superposition is gone for that property. The measurement has fixed a state.
So measurement is this bridge from the probabilistic quantum world to our definite classical world, involving amplification and irreversibility.
That's a good way to put it. It's a physical, irreversible interaction that converts quantum possibilities into classical facts.
Okay, so let's circle back then. We started because this experiment is so often linked, especially in pop science or certain philosophical circles, to consciousness. Given everything we've unpacked, what's the actual scientific consensus on that link today?
The overwhelming mainstream scientific consensus is that human consciousness does not play a direct role in collapsing the wave function or determining quantum outcomes. The observer in quantum mechanics is the measuring device, the physical interaction, not the mind of the scientist looking at the results.
So the von Neumann-Wigner interpretation, the idea that consciousness is the thing that collapses the wave function, is not widely held.
Not really, no. It's a historical viewpoint, an interesting philosophical position, but it's not what most working physicists subscribe to or find necessary. They generally believe quantum mechanics, and even future theories like quantum gravity, can be fully explained without invoking subjective consciousness as a causal element.
But our sources did hint at some ongoing debate, maybe some alternative views still kicking around. It's not completely settled for everyone.
That's true. While it's definitely a minority view within physics, there are still researchers and thinkers who explore the connection between quantum mechanics and consciousness. It hasn't vanished entirely.
Like who? What kind of ideas are out there?
Well, you have people like Donald Hoffman, for instance. His idea is quite radical, suggesting that space-time isn't fundamental, but that consciousness or conscious agents construct or render reality, perhaps similar to how we render a virtual world on a computer screen. Our perception isn't just observing reality, it's actively creating our experienced reality.
Wow. Okay, that's a very different picture.
Very different. Then there's a Bernardo Kastrup, a philosopher and computer scientist who argues strongly against physicalism or materialism, adjusting instead that consciousness is fundamental, that the universe is essentially mental, and physical reality emerges from consciousness, not the other way around.
So turning the common assumption on its head.
Completely. And then, perhaps more directly related to the double-slit specifics, there's that recent work from Hiroshima University you mentioned earlier.
Right. What did they find? It sounded intriguing.
They developed a clever technique using polarization, the orientation of light waves in the slits themselves. They claim they can get which path information, know which slit the particle went through, without completely destroying the interference pattern.
Wait, how? I thought getting path info always destroyed the interference.
That's the standard understanding based on strong measurement. Their approach seems to involve a gentler measurement, extracting partial information. Their results, they argue, suggest a genuine physical delocalization. The particle is truly spread out between the slits. And crucially, they interpret their findings as strongly indicating that how the particle behaves at the slits can depend on measurements performed later in the particle's journey.
So more fuel for the delayed choice fire.
It seems so. They're aiming to build a more inclusive picture of quantum mechanics, explicitly questioning how measurements can shape the past of a quantum object. It's ongoing research, but definitely pushes the boundaries.
It really feels like we've peeled back layers of an onion today. From the basic wave-particle puzzle of the double slit, to the observer effect, then delayed choice, the different interpretations.
Yeah, Copenhagen versus realism.
What measurement even is, and finally touching on these consciousness links. Both the mainstream dismissal and the alternative fringes.
It's a lot to take in.
It really is. It's clear this isn't just some quirky demo physicists play with. It's a profound, fundamental challenge to our most basic common sense intuitions about how reality actually operates.
Absolutely. If you walked in thinking reality is just out there, fixed and objective, waiting for us to find it, this experiment really forces a rethink. The act of observing, of interacting, seems inextricably linked to what becomes real.
So that final thought then. If measurement defines reality, if future choices might influence past quantum states, what does that really say about this moment, our now? Is the reality we experience every day as solid and fixed as it feels?
Or is it constantly shimmering, unfolding, a quantum dance where interactions, maybe even our future observations in some strange way, are continually shaping what is? Is the now less of a fixed point and more of a constantly resolving quantum state?
That is definitely something to chew on long after this deep dive ends.
Indeed it is. Makes you look at the world a little differently, doesn't it?
It certainly does.
Okay, there's a human in the loop if you want to chat about this. We're trying to improve the tool as well while listening to the professional podcasters. So the tool works pretty well. Yeah, there's a few things that I would have done differently. Now we have the observer on-off button as well. You can fire a wave again. It will show you the difference between the two. Overlaid in demo mode. Yeah, demo mode, it clears the simulation every time. Yeah, so notebook and lamb conversation. We have another sources about the link to neuroscience. So it's quantum theory, double-slit experiment, and link to how the human brain works. So it'll be talking about that next. Well, still, there was some bug that I noticed, but I don't remember what it was. Do you remember what it was? Yeah, so if you separate the slits, you will get more of those waves. Reduce the slit width as well. So now we have, no, still 3. What? Wait, if we have like slit separation. What's up? Wait a sec, there's something wrong. Oh, when resetting it resets the settings as well. Okay, we have to. Okay. Now we should have, was it 4 or 5 or 6 different distributions. So that seemed to work okay. By the way, everything we do is available on BioniChaos.com. Go check it out. We already have that tool deployed, but yeah, currently doing some improvements to it, making it better. Well, the demo thing was not. The demo thing was not working. So hopefully now we fixed it. We just have to redeploy the website. So the website will be down for like a few seconds. During that time we can just listen to Notebook LM. Still generating the conversation. Takes some time. So we're talking about the quantum physics and neuroscience. How good is that? Yeah, in the demo mode, it's not actually firing enough particles for you to see the distribution. The whatever 500 is not enough. Now you see distribution more clearly. When you hit observer on, then becoming predictable. So essentially when you have a detector on the slit, the fact of you measuring something is affecting the behavior of the particle. So before, if you do not observe it behaving like a wave, if you do observe, it starts behaving like a particle. So it's going through one of the slits. If you do not observe, it seems to behave like a wave where it's going through both the slits. One thing going through 2 places at once. How crazy is that? How crazy is that? Yes, you can see. Why is it moving so fast? Oh, and we have a music as well. So the canvas actually has a frequency tied to it. So that will be higher frequency. That will be lower frequency. When you fire a wave, you get music, quantum music. So that's, what is it, Mozart meets Schrödinger.